Good day. Welcome to Physics for Engineers, and today's lesson we will discuss about oscillation. Our running objectives are to understand the concept of oscillation, to describe the motion of simple harmonic motion and its reference circle, and use energy concept to analyze simple harmonic motion problems. Our topic outlines, we will describe the oscillation, and then we will discuss the ideal spring and simple harmonic motion, and then the reference circle, and finally, the energy in simple harmonic motion. Oscillation. Many kinds of motion repeat themselves over and over. For example, we have the vibration of a quartz crystal in a watch, the swinging pendulum of a grandfather clock, the sound vibration produced by a clarinet or an organ pipe, and the back and forth motion of the pistons in a car engine. So this kind of motion or repeating motion is what we call periodic motion or oscillation. So in this lesson, we will focus on the simplest kind of oscillation, which is the simple harmonic motion. So to have a better understanding of the topic, I found this simulation in the internet at iwanttostudy.org. I will post the link at the description below so you may visit and explore this simulation. So this is the simplest system that we can have a simple or we can have a periodic motion. We have a body with a mass m that rests in a frictionless horizontal plane or guide system so that it can move only along the x-axis. So the body is attached to a spring of negligible mass that can be either stretched or compressed. The left end of the spring is held fixed, and the right end of the spring is attached to the body. So the spring force is the only horizontal force acting on the body, while the vertical, normal, and gravitational force always add to zero so that we can have a displacement along the x-axis. So it simplifying our coordinate system so that at origin point O, at this center, is the equilibrium position. So when the spring is neither stretched or compressed, then we will have a displacement along the x-axis, or we have an x component of the displacement. It also changed the length of the spring. So the x component of the force that the spring exerts on the body is Fx. And the x component of acceleration is given by Ax. And following the Newton's second law of motion, we have Ax is equal to Fx divided by the mass of the body. So in this illustration, if we move this body at point 2 meter, let's put it 2 meter to the right. Yan, 2 meter. So whenever this body is displaced from its equilibrium position, the spring force tends to restore it to equilibrium position. So we call the force on the spring as restoring force. So oscillation can occur only when there is a restoring force, tending to return the system to equilibrium. So let's try to play the simulation. Okay, and pause. So to analyze how oscillation occurs in the system, if we displace the body as like we have did to the right or to the left, either way, then a net force and acceleration are going to produce or generate. So in this case, we move the body to the right, therefore the force and acceleration will be directed to the left. Then the speed increases as the body approaches equilibrium. Okay, let's see. So starting here, we have zero velocity and we have initial position of 2.0, and we know that the point of equilibrium is at point 0, wherein the spring is neither stretched or compressed. Then we will observe that the ball velocity as approaches to 0 increases up to its maximum velocity. Let's see. Okay, once more. Okay, so we have here the maximum velocity is 2 meter per second. Meanwhile, it will, we can observe that the minimum, or we can observe that the velocity at point A at 2 meter or point B at negative 2 meter, oops, is nearly 0, up to a point that it has a 0 velocity. Let's see. Yeah. So meaning our body is stuck at point A and at point B. But because of the restoring force that tends for the spring or for the body to go to equilibrium position at point O, it will overshoot. Okay? So this example of our oscillation or periodic motion. So it repeatedly moving back and forth. So in this case, this is a real spring. We have a frictionless surface, meaning there is no force that will oppose the movement or the motion of our body. Therefore, it will move infinitely back and forth. But if there's a friction force or an external force that will oppose the motion, it will um, it will eventually going to stop. Now, let's describe this oscillation or periodic motion. Okay, let's restart. And let's move our body at point 2 meter. And this time, um, we will observe how the graph of the position versus the time of our body. So on the right side, we have our coordinate at the position x at every seconds. So we're going to play. So what we can observe with our graph, Now let's continue the simulation. So as we can observe, we can say that infinitely it will move back and forth from 2 meter down to 0, then negative 2 meter back to 0, then 2 meter, then down to 0 and negative 2, and so on and so forth. So now we will describe, or how we're going to describe our oscillation motion. So first, let's define the amplitude. Amplitude is the maximum height or maximum displacement that our body can move. So in our case, our maximum displacement is this one, and the symbol for amplitude is A. So in our case, our amplitude is equal to 2 meter. So if we're going to measure from point A to point B, so this is what we call our range. So in our graph, we can see that the amplitude is represented at the maximum height. Yes, our amplitude. So amplitude is always has a positive value. We have no negative value for an amplitude. So it's always an absolute value. Okay, the next, let's have the period. So we know that oscillation is also called periodic motion because it has a period. So what is period? So period is the time for one cycle. So what is cycle? Cycle is, we can say that the one cycle is when our body or our object go back to its original position or initial position. So in our case, so from time 0 to time 6.28 seconds, this is our one cycle. This whole motion of our body is our one cycle, meaning when it makes its one whole motion. So we can see that it started from 2 meter, then go down to negative 2, then back to 2 meter. And at this point, it will repeat its motion again from 2 meter down to negative 2, then so on. So this is our one cycle. So this part of this our graph is what we call cycle. So this is one cycle. And period is the time it takes for one cycle. Therefore, its unit or it measure in seconds per cycle. So in our case, in this illustration, we have our period of 6.28, and the symbol for period is T. Now, let's define frequency. So frequency is the number of cycles in a unit of time. So frequency our symbol is F, is the reciprocal of period. Again, so frequency is defined as how many cycles it can take or it can have within 1 second. So in this case, our illustration, we can define frequency, or we can get the frequency by the reciprocal of 6.28. And the unit for frequency is hertz, or in symbol, Hc. And lastly, we have the angular frequency. So angular frequency is the rate of change of an angular quantity, meaning how many rad angle it takes within a second. So how fast the angle of our periodic motion changes in measure of time. So again, we have these four quantities important to take note. First we have the amplitude, then we have the cycles, period, frequency, and angular frequency. So in describing oscillation, we know that a motion repeated in equal interval of time is called periodic motion or oscillation. Then we have the amplitude. We define the amplitude as the maximum magnitude of displacement from equilibrium. That symbol is A, and it is always in positive value. Then we have the period, or T, which is the time for one cycle, or seconds per cycle. And then we have the frequency, which is the number of cycles in a unit of time. It is measured in hertz, and it is the reciprocal of period. And lastly, we have the angular frequency, and the symbol for angular frequency is a small letter omega, which is the rate of change of an angular quantity. And to get the angular frequency, we have this formula. Omega is equal to 2 pi f, where f is the frequency. Now that we have able to describe oscillation motion, let's have an example problem. So our problem, an ultrasonic transducer used for medical diagnosis oscillates at 6.7 megahertz, or 6.7 times 10 raised to 6 hertz. How long does each oscillation take, and what is the angular frequency? So in our problem, we have our given, which is a frequency of 6.7 megahertz. And we're looking for how long does each oscillation takes, which is period, and the angular frequency. Now, to solve for the period, we know that period is the reciprocal of frequency. So we're just going to divide 1 over 6 times 10 omega hertz. Therefore, our period is 1.4925 seconds. So to have one cycle or one period or one oscillation takes is 1.4925 seconds. Next, for the angular frequency or the rate of change of the of the um, of the angular quantity, we have the formula 2 pi f. Therefore, our angular frequency is 42.097 times 10 raised to 6 megahertz. Oh, sorry. So over, so we can now erase the times 10 raised to 6. We just simply write megahertz. Okay, so that's it. Now it's your time to shine. So let's try to solve problem and have your test your understanding. So we have here the problem and a graph, and try to solve and write your answer in the provided comment section.